Well, thank you. This is, of course, episode 2 of our QA Science post-lecture QA session. We're here with local teachers as well as honors students in the UA Honors College. My name is John Pollard. I'm going to moderate this. And of course, we're talking to Professor Feryal Ozel. And I want to start off by just making a comment and sort of a question. How do you operate in your everyday life knowing these things? I mean, that shot of the moon when it was panned back, I don't know what everyone else thought, but I was sort of left in a state of shock at the magnitude of the universe because it kind of gave this impression. And my very first thought was having this knowledge and sort of dwelling in that realm of your research. And then you have every day, like you have coffee or something. I mean, how do you bring these two worlds together?
Yeah.
What's
I
it,
mean,
you know?
to be honest, on a day-to-day basis, I don't think about the scale of the things that I'm working on. If we did, I think we would go slightly crazy. I mean, we being like people who work on different parts of the universe and things far away, and they, like you said, the Hubble Deep Field, Chandra Deep Field, black holes that are far away from us. I mean, I am usually just caught up in the whatever's in front of me. But once in a while, it does hit you that like I'm 10 minutes late to something and I'm stressed out and what, and you're like, oh my God, like I'm truly a speck of nothing. And I'm just continually, rushing against time and whatever. And it's like I'm on a tiny planet in a vast universe, living for a blink of time. And of course, but that's not how you live. I mean,
Yeah.
that's not how you live. You have to take your kids to school. You have to make your coffee so you're
Yeah.
awake, and there's bills to pay and all of that.
Yeah.
So yeah,
All right. Well, I just had to
yeah,
ask that as to start this off.
yeah.
I think we have some mics in the audience. I think we're just going to open it up here. Do you want to hand the mic over here to Jacob? And we'll just kind of go around. Please hold the mic up and go ahead, Jacob.
So what more kinds of information do you expect to glean from the Event Horizon Telescope, given what you've already gotten over the past 20 years? Is there any more to find with the current technology?
Yeah. So what I showed you, that time-lapse movie from the last 20 years, is stars that are, okay, we say close to the galactic center, but really they are quite a bit farther away. So by following their motions, we can say there is a mass interior to those orbits, but it doesn't tell us what the nature of that object is. So with the event horizon, we're going much, much closer. So um, we would be going probably 6 or 7 orders of magnitude closer, like 1,000,000 times closer than where you see those stars. The Event Horizon Telescope, this image that we're trying to obtain, is 1,000,000 times closer, and that's why we are able to resolve. I mean, the technology allows us to resolve the horizon scale.
Thank you.
Another question. Why don't you hand the mic right there? Thank you.
Hi. I know there's a lot of critics who say, kind of ask the purpose of this research. And so I kind of want to ask, what would be your rebuttal to people who say, what's the point of giving more funding to research like this as opposed to maybe like climate change or education?
So when Einstein formulated his theory of general relativity, rewriting the laws of gravity, we certainly did not think our GPS devices would need it to run, right? Our GPS devices continually correct for the Einstein time delay. Otherwise, they would very quickly become futile. And I mean, like GPS has changed our lives. Everybody can find their way now. Um, when people worked on coherent light sources that then became lasers, it was a purely theoretical study. Not one person thought, I might have eye surgery one day using these lasers. No, it was a purely theoretical expedition. It was like, how does light behave? How does it become coherent, etc. But having said that, and I can give you many more examples of Teflon, of this, of that. I mean, it's just so many unintended consequences of basic science. It happens all the time. That's not the right answer. That's not why I do it. I think we do it because we're curious as human beings. And we do it because it brings meaning to our lives, to understand the world that we live in, the universe that we live in. We create art. We explore. We do philosophy. And so I think scientific exploration is just a basic human need. And even though I could give you that answer about there are so many unintended consequences and benefits and spin-offs and whatever, that is not for a single day why we do it.
Great. Now let's hand the mic. Well, why don't you ask a question first, and we'll hand the mic back. Go ahead. Yeah.
So, what do you think finally getting direct evidence, like a picture of a black hole, would contribute to the field of science?
I can sleep after that. I think it will just be a feat, right? To look at something that far away, to make a specific prediction about what its properties should be, that there should really be a hole in the sky among the light surrounding it, because gravity is so strong in it. There really is an event horizon. Like, there is an information loss. There is light and matter and stuff crossing it and disappearing from the observable universe. That, like, there's a point of no return. I think it's going to be amazing. But really, like, at the end, I was half joking at the talk, like, what if Einstein is not right? Actually, I mean, that would be a very exciting possibility. What if there is, and I don't mean like the experiment doesn't work. The experiment works, and what we see is not exactly what we predict, that there's a deviation from it. And we have to now revise Einstein's theory and maybe give us clues about how we can marry it with quantum mechanics. I mean, the possibilities are endless. So, but it's just curiosity, really.
Yeah, hand the mic back. Thanks.
Okay, after having to organize so many star parties at schools and being dependent on weather, what are the logistics behind you getting these 5 days worth of data in these places across the world? How did you guys plan that? Do you have dedicated scopes, or you just had a certain amount of time? Or
Thank you for asking that question. That is one of the major challenges of this experiment. So one thing is getting the telescopes everywhere, and the other thing is coordinating the observations. So we have historical data on what the weather on different sites are like. So we chose the time of year that optimized it. So we said, okay, end of March to end of April time period tends to be good weather in all of our locations. South Pole is always good weather. Chile, the Atacama Desert is almost always good weather, like very high, very dry, and just usually good part of the world. Tucson, as you know, or Mount Graham, has variable weather. Our LMT telescope in Mexico has variable weather. The Alps have so there we just relied on historical data to find a window. A lot of them are dedicated telescopes, not dedicated to this project, but at least work on a, hey, we need the telescope from this day to this day. Can you make it available basis? One telescope that is not like that is ALMA. It is a heavily oversubscribed, huge telescope that researchers around the world want to use. So for that one, we actually write proposals. They get peer-reviewed. We get the time. And then we say, we'll give you a 10-day window, and then we'll trigger or not trigger. And then a bunch of us sit in a control room. Like, a lot of my colleagues are at telescopes actually doing the observations, and a bunch of us sit in a control room getting real-time data, sometimes the telescope will have a problem, like the tracker won't work properly, or the one of the discs failed, and or whether it was too windy to point. Like we couldn't stably point because the wind on one of our sites was so strong. But every night, in fact, like around 3 p.m., we sat down, we collected the data from all the sites, and we said, does it look good enough? Like we called it a go or no go decision. And in 2017, we had go decisions back to back. In 2018, we had a lot of no go decisions because the weather just wasn't as good. So, yeah.
So your 5 days or nights of data, they're not consecutive, they're over a certain period of time? Or?
In 2017, 4 are consecutive. The 5th one is 3 days later. In 2018, we again were able to observe for nearly a week, but it was in bits and pieces. And not every observation involved all the telescopes. So we said, okay, we don't have this one, but let's do it anyway.
Just as a follow-up here, before
Yeah.
we go to another question to answer, what is the nature of this data that you're evaluating that comes in? I mean, what does it, is it numbers, is it images, or what are you actually making a judgment call on?
So the raw data literally is a recording of every wavefront. So electromagnetic waves, as you know, have the sinusoidal feature. And whether this is millimeter waves or X-rays or what, X-rays, okay, we count photons, but in radio, it's just ups and downs of a sinusoidal wave, and we record it. And the reason we generate so much data is because there are 10 to the 9, a billion cycles every second. So when you calculate the frequency corresponding to that wavelength for the speed of light, it is a billion cycles. So every second, we have to record a billion of those cycles. So why do we do that? When you record it so faithfully, so you can have individual waveforms from one telescope and individual waveforms from the other telescope, because they're at different positions on Earth, light arrived at them at slightly different times, so there's a time delay. You match them up. You basically search on this wave train and this wave train on a supercomputer, how much do I need to shift it by so they completely match up? And that's what like this interferometry technique relies on, or synthesis.
So it's an
relies on.
actual visual evaluation of data, sort of, like you said, the wave formation that's forming at some resolution.
Yeah, of light at a millimeter wavelength coming in, and all the waveforms being recorded in each of the locations. And that gives you, like, think of it as if it were music. Each pair of telescopes would give you one note. So you want so many different pairs that you hear all the different notes and you put the music together from it. An image is very much like it. So each pair of telescopes will give you one component of the image. And then we put all of it together, and that synthesis of data is the full image then.
Interesting. Sandra, do you have the mic? Yeah.
Yeah, so I'm going to go back a little bit. In this lecture and your previous one, you talked a lot about your excitement of failure and talking about how it's a really positive thing. So how do we as middle school and high school teachers instill that in our students too, that science is a lot of part of failure, without increasing that doubt within the field of science? How do we get students to see that failure is really necessary in that field without casting more shadows that we often see in like current media in the field of science?
Yeah, I think we should honestly talk about the uncertainty and our desire to quantify that uncertainty and to design experiments to reduce it. And it's one thing if you design the experiment, it works as expected, and there is a negative result. So I think we should just say that is valuable too, that science moves forward when you have experiments that give you negative and positive results. In the field of medicine, for example, there's a huge problem that scientists don't publish negative results. So it biases, like it actually makes you think the result is different than it is. We publish negative results as much as possible. There isn't a stigma attached to it. But ultimately, I think just being honest about this is how science works, and we are not after dogmas. This is an experimental field, and just be smart about how you're designing the experiment so you can get an answer, whichever way the dice fall. Yeah.
Okay, we got a lot of questions. Let's go over here first. We'll come back. Let's go hand it to Sarah, and then we'll transition over. Go ahead.
I had a quick question. You mentioned information being lost in a black hole, and I'd read about there was some sort of debate between information being lost versus information being preserved. What exactly is meant by information when this is said?
Information is anything. So the simplest way to understand this is if you take a lump of coal versus an encyclopedia and throw it into a black hole, there is no way to reconstruct from any signal, any type of like any observation that you do after the fact, of being able to tell whether it was a lump of coal or an encyclopedia. So, I mean, encyclopedia, of course, here is the representation of all information, but you lose your any knowledge of what fell in to the black hole. It just becomes that singularity, that energy, that mass. Event horizons do indicate an information loss. Even then, there are some versions of string theory, which we can't test right now, but we are certainly trying to understand and trying to find where it meets astrophysics, that say information gets stored in effectively what you would call the skin of the black hole. There would have to be certain predictions of that differ from information as being lost. And based on those predictions, then we would know what observations to do. And yeah.
Okay, let's hand the mic over and we'll come back over here. Let's go first to Kat and then we'll come back over. Is the mic over here somewhere? Yeah, okay, you got it. You're next. Go ahead.
So the title, like dark, that goes with dark energy and dark matter. Does that refer to it being actually dark as in the absence of light, or more that we're in the dark about what it actually is?
Very nice question. In dark matter, it actually refers to matter being dark, as in the absence of light, that it does not interact with light. It doesn't emit it, it doesn't absorb it, it doesn't have any electromagnetic interaction. In the case of, however, I mean, even there you could say part of the pun is that we are in the dark about what it is, because if it's made up of particles that we've never seen and we don't know the nature, like we don't know what is the mass of dark matter, I don't know. How was it formed? Is it supersymmetric? Was it formed in the early universe? I don't know. So, I mean, yes, there is also a lot of that. With dark energy, I would say it primarily refers to we don't know the nature. Because it's not, I mean, energy doesn't emit light anyway. It's just a completely different form of energy that is repulsive, that causes the universe to expand faster and faster. So there it's far less about light and more about, I don't know.
Let's go over here first, yeah.
I really loved how your talk is grounded in the basic rules, the foundational concepts of physics in our world. I guess you're saying it how it helps you interpret what we see. So conservation of matter and energy, maybe the name black hole makes me think of a hole that something goes into. I think you maybe answered it a little bit. Maybe this information goes to the skin of it. But I was wondering, if you picture it, if you actually find this event horizon, do you then begin looking for where this matter and energy goes? Are you looking for some black fountain someplace where this energy goes, or?
So, as far as conservation of just mass and energy, forming a black hole doesn't violate it. You you take whatever matter there is, you throw it in there, it adds to the mass of the black hole. So you're not losing it. So there is conservation in that sense. But it is going to a place where it's disjoint from the rest of the universe. So you're losing information means all our laws of physics, if I just change the sign, it would go the other way, right? I mean, I can have interactions that produce something. I can have interactions that combine the same thing, like in particle physics. I can have interactions that make things move one way. If I reverse time, it will go the other way. You get to a point where you don't violate mass and energy conservation, but you certainly violate the reversibility of your physical laws. You can't say, oh, now the black hole is going to spew things back out if I just change the direction of time. So, yeah, that breaks.
Let's go over here and then hand that mic up. Yeah, go ahead.
So you mentioned like the reversibility of the physical laws, and I was wondering if you think that adds or takes away from the reliability of these laws, or if it's kind of irrelevant.
I think it's a very basic feature of our laws. I think back in Newton's times, we built laws one at a time by experimenting and, trying to fit an amount of data, whatever it might be, planetary motions or how things fall to the ground or whatever. Now we approach physics from almost a more philosophical point of view. Like we first put down some symmetries that we want our laws to obey, time reversal being one of them. And we say, okay, how can I formulate an equation that certainly has desired properties as far as nature goes, but above and beyond that, how does it mesh with other things I know about nature? So I think it's an attractive feature.
Okay, yeah, good one. Go ahead.
During your talk, you showed 6 different predictions about what the event horizon of a black hole might look like. What were the differences that we looked at in each one of those 6 predictions, and what was looked at specifically for the University of Arizona's prediction and movie?
Very good question. So there are things we understand quite well about black hole environments if they are truly black holes, and there are things that we can't quite model. So we know that a lot of the matter that ends up falling into a black hole comes from nearby stars. They lose mass. There's like winds of mass leaving from stars. They come near the black hole. They have angular momentum. They settle into some sort of a disk. It's like a spiraling inward motion. We know the basics of how that works, but we don't actually know, for example, en route to the black hole, what temperatures they heat up to. We can have, for those of you who have taken thermodynamics, we can make some arguments about what those would do, what temperature would they get to, some basic energetics arguments. But there are a lot of subtleties to it. There's a magnetic field there. How does that affect things? There is, when the gas is very dense, how does that behave? When it's very rarefied, how does that behave? So there we have to resort to our best guesses. And those were meant to be a gallery of both different groups working on this problem. How does gas fall into a black hole? How does it shine in the meantime? What temperature does it reach? And each group built a slightly different model in order to explore the unknown aspect of it. So if we put all our money in one basket and design an experiment around it, we can be surprised in an unpleasant way. But if you at least say, this is what I understand, this is what I don't know very well, but I'm just going to keep on exploring among these possibilities if there are any showstoppers. So that's what we did there.
All right, let's go here first. Go ahead.
So, this might be kind of like a little fictional or Star Trek-y in a way, but what kind of prospects do you see like black holes being served as in like space travel? Because there's a lot of like theories out there that it could be like a wormhole and that like you could do things with that.
Yeah.
How much merit do you think those theories hold?
Not very much, sadly. So there are mathematical solutions to general relativity that probably don't play out in nature. Like the simplest equivalent of that would be like solving a mathematical equation. You get an imaginary number, you get a negative number, and you say, oh, well, I'm just counting apples here. It can't be negative. General relativity equations have solutions like that too. And most likely, I mean, for example, time loops, right? They're allowed. They're illogical. So a lot of the Star Trek-y things that we see about black holes are those most likely not applicable to nature solutions.
But time loops would make for good sci-fi.
I mean, it
Definitely.
does, right?
Yeah,
It does,
that's
yeah.
good stuff right there.
Yes, you go kill your father kind of thing.
Yeah, who's got the mic over on this side? Okay, Sophia, why don't you go there and then we'll hand the mic back. We got a lot of demand. Go ahead, Sophia.
Quite often throughout elementary, middle, high school, college, we're told that the universe is expanding. But as far as I'm aware, we have no concept of the bounds of the universe or how far it extends or how large it is. So how can we measure how a substance or a phenomena is expanding if we don't know how big or small it was to begin with or where its limits are?
Okay, that's a good question. So imagine a balloon and imagine when the balloon is small, putting dots on it. Okay, so dots separated by some distance on that balloon. And now start blowing up the balloon. Okay, every point on the surface of that balloon is moving away from every other point. So the stickers that you put on the balloon initially, these two are farther apart, these two are farther apart, these two are farther apart. So when we say the universe is expanding, we mean the fabric of space-time between them is literally stretching out. Now, if I had a full balloon and I could look at it from the outside, I would see that it's expanding, right? Every dot I put it at the beginning is moving away from every other dot. But even if I couldn't see the whole balloon, even if I had just a subset of the data, I could still see the dots are moving away from one another. So when we look at galaxies in the observable universe, which is not the entire universe, I mean, it's just what we can observe, how much light has traveled during the age of the universe. Every galaxy, not every galaxy, of course there are close pairs of galaxies that are not being ripped apart, but galaxies are moving away from each other. So even with that kind of data, you can tell. You don't know where it was before, but you know they're moving away from one another.
And is there potential that even though everything's moving away from each other, if we could zoom out a whole lot and see the entire universe, that the physical size of the whole thing wouldn't change?
I think what we mean by physical size is a little bit different. So it's not that the sizes of galaxies are changing, but the time it takes for the light to go from one galaxy to the other is changing. It's just becoming longer and longer. In our future, we will remain close with Andromeda, but probably we will get to a point where we won't see any other galaxy because it will be just too far away for light to reach us within a universe time, which is a sad thought. We'll be so lonely. I mean,
as we hand the mic back, I want to give Eric a chance in the back, then we'll work it back up front. But just as that mic's being handed back, I want to just follow up on a question there. Am I correct in my thinking here that in that balloon analogy, then no matter what point you are in the balloon, you are the center, sort of, you have the feeling of being at the center of the expansion? Is that how that goes? So from our perspective, we see everything expanding out, but from every other perspective, it's...
Sure.
Yeah, okay.
Exactly.
Okay.
Sure. Yeah, I mean, the balloon analogy is a little limited because it is intrinsically two-dimensional, right? Like I'm describing a surface rather than a volume. But it is true. I mean, from every point in the universe, you see things moving away from you. So from that point of view, that analogy is successful, and you're interpreting it correctly.
Okay. All right.
All right, so black holes, you know, we love them and we want them to like take things somewhere or whatever. But as they add stuff, right, they get more massive. So they're collecting the stuff they were made out of, and now they're sucking up. Now, you learn about matter, how it's almost all nothingness. So can you pack it? I mean, they talk about a singularity. Is it a singularity like an actual no space, or is it just so much energy that it can actually take all of that nothingness and take the stuff in the nothingness and pack it into some tiny space? I mean, is that even a question?
I don't know. I mean, when we say a singularity, we mean the former. It literally occupies no volume at all. It is infinitely condensed, just like the Big Bang was at the beginning of the universe. All that energy and mass is condensed in a form that we don't know, we wouldn't be familiar with, into an infinitesimally small space. So it's not small, it is infinite, like it just shrinks to nothing, although that energy and mass is there. Is that true, or does it actually turn into something else that stops that collapse? I don't, I mean, one of the reasons for looking for horizons is that. I mean, a singularity behaves different than alternatives to it. Yeah.
Yeah, go ahead, right there.
So in your lecture, you touched briefly upon the idea of the gravity around a singularity warping the space-time continuum. I was wondering if you could go more into detail about that.
So every object with a mass warps the space-time continuum around it. So it's not measurable, but our bodies warp the space-time around it. The Earth certainly warps the space-time around it. I mean, that's why we need to do GPS corrections, right? Like we need to do general relativistic corrections to the GPS signals from satellites that are orbiting the Earth. The sun warps the space-time around it in a pretty profound way. You see the positions of the stars shifting during a solar eclipse when the sun is in front of you, and you can see the star through that mass, versus when the sun is in the other hemisphere and you see the stars directly. So these are all measurable effects, except for the warp that our bodies cause, for example, or like a small object causes. In a singularity, it just becomes extreme. It warps it so much that there is a volume in which all paths are pointed inward. So around the sun, the paths are the trajectories of matter and light and sunlight, starlight behind it, whatever. They're bent, but they're not bent so much that they turn inwards. Around the singularity, they're bent so much that they turn inwards, so they're trapped there. So that's the difference between those cases. I don't know if that helps with the question.
A little bit more about the time aspect of the effect of the gravitational force as well.
It is going to be quite technical for this conversation, though. So right at the horizon, actually, what you call the space coordinate and the time coordinate flip. So that's why all trajectories point inward. So that we can separately have a space direction, like I'm walking towards John here, and I can have a time direction, like time is running towards tomorrow, or like I have control over my direction as a function of time. At the horizon, I don't anymore. I mean, there's a flip in the equations that basically points to a direction as if that is the direction that time is flowing in. But without doing the math, it's a little bit abstract.
So,
describe it that
you
way.
couldn't verbalize that by saying that the analogy you just used, like, okay, you're walking towards me, and there's a time that just feels like it's going regardless of whether you're walking towards me. So the opposite would be
I'm
you're-
dragged with the current.
You're
Yeah.
controlling the time,
Mhm.
and the space is just you're just
Yeah,
you can't
yeah,
do anything
yeah.
about it.
I mean, it's like if the current is mild, I can swim across it. Maybe I can swim against it, but it's a waterfall. So if you're caught in a waterfall, your future direction is pretty set, right? I mean, it is going to be downhill. So that's the closest analogy we usually come up with, like a river or running water or something like that. Yeah.
Yeah, let's go over here, Eric.
So I had a educator question, and you've handled some of these really well. But how do you get to some of the wonder that science inspires without getting into too much of the woo about it? Just thinking about the other day when we had a lunar eclipse, you couldn't read about it in the news without seeing the words wolf and blood in there. And
Right.
like gravitational lensing, if we had a solar eclipse a few years ago, I didn't hear a single peep of anybody saying, oh, check out the positions of these stars.
Yeah. Yeah. I don't know why we water it down so much. I mean, it is fascinating. I mean, we don't have to talk about every detail, but the discovery aspect of it is really fascinating, right? I mean, like, we don't hear how often do solar eclipses happen. Like, just what is the geometry of the sun, earth, moon system that causes these eclipses to happen, and how often? Like, we only hear about it. It's visible from North America, like, only once every, like, until end of 2020, it won't be visible, whatever. It's like, that's not the piece of information I'm interested in, right? So I don't know. I think our coverage of everything has become a bit sensational. But as science teachers, I think you have the ability to ground it a little bit more. I mean, yes, it is super fun to look at it and just like see that disk moving across the moon and it's slowly disappearing and reappearing. I mean, it was very nice, but yeah, it wasn't like wolf and blood and this and that. It's just, I don't know. I mean, I think you have the ability and the media doesn't.
Hand the mic up here to Annie, and then we'll go over here, and then we've got, Maura. Yeah, go ahead, Annie.
So the discovery of black holes is a fairly recent event. So how much do you think is still completely unknown about the universe? And do you think we can ever discover everything?
The discovery of black holes dates back to the 60s. Before that, there are theoretical discussions about them. Like, it's obvious that the one of the solutions of the equation is a black hole. In fact, the first solution discovered, the Schwarzschild solution, is 1915. I mean, like months after Einstein's formulation of the theory. But from that, I mean, you can always dismiss it as this is mathematical. Like it's not going to happen in the universe. In the 60s, when we started seeing bright quasars that are at large distances, and we saw that there's just a lot of power coming out, not from the hole itself, of course, but from gas being like falling down those potentials and just emitting a lot of light. That's when it became a reality. Will we ever know everything about the universe? Probably not. And I think we'll keep on looking, exploring, testing, but I don't know how you would ever say, that's it. I know it all.
Could you hand the mic over here? Then we'll go to you more.
So you mentioned you're in search of the horizon, which is still like a theoretical concept to this date. So what if you conducting your research do not find the horizon? What does that mean, and what are the steps from there?
So if we don't find a horizon, the first thing that we're going to do is try to figure out what we may have done wrong with the experiment. We say we picked a particular wavelength where the gas should be transparent. Is it that it was opaque and it's just, I mean, the horizon is there, but it's obscured? we'll go through possibilities of telescopes malfunctioning, of our theory being incomplete, or not theory of the black hole itself, but everything around, like what we were talking about. We think we ran a whole suite of simulations to quantify what we don't know. Maybe we didn't do a good job. So we'll go through all the mundane possibilities first. Things malfunctioning, our predictions being incomplete, our reasons why we didn't see what we were expecting to see. If we convince ourselves that it's none of those things, then you're left to consider the possibility that the horizon is not there. So a black hole does not have a black hole in its image. So then you say, what could it be? I know that it's a very compact object. It's for example, for our own Milky Way black hole, 4 million solar masses in an orbit that's smaller than the solar system. I mean, what would happen to all that mass? You start going through the alternatives of what else it could be. But frankly, first we're going to search for like what could have gone wrong.
Let's go to Mauro. Pass that back to Josh. I think he had a question too, and then we'll go to you, Van. Go ahead, Mauro.
So it seems like a lot of physics isn't really based in observable evidence. So when you're doing that kind of theoretical research, how do you even start that process?
I think you start with a framework anyway. You either start with the framework of the data that you've already collected, like Copernicus did, like Kepler did, like Newton did, or you start from, I know this theory is proven, it makes such and such predictions, so it's more like thought experiments of, okay, if I take this now and apply it to this situation, what would happen? So there are methods. I mean, you're not literally sitting there thinking, what equation should I write? I mean, it's not like that. It's really an extension of an existing framework, whether this is data-driven or symmetry-driven or something in between.
Josh.
First of all, thank you so much. I think you're kind of a master of analogies. And I think maybe that's partly because of your field, but also I think that teachers really try hard to create analogies all the time to get students to understand things. But I think they have a very hard time doing it themselves. Could you speak on like kind of the power of creating like mental models, or even making models on boards, or even doing these supercomputing kind of models? I think it's a really powerful idea in education. And I find our students, they'll quickly go to a cliff and then just kind of give up.
I completely agree with you. Mental models are very, very important. In fact, I recently read a book, maybe some of you have to peek, like how people learn. And it's not just in science. The book is arguing that we build mental models in anything that we learn, whether this is a golf swing or chess or, I mean, they experiment with memorizing numbers. And these two authors who are neuroscience researchers, as far as I remember, they talk about, I mean, how you basically build a mental picture of what you're studying, what you're trying to learn, what you're trying to develop. Like, how does that feel? How does I don't play golf, so I mean, I'm making it up, but how does my tennis swing feel? Whatever. And certainly working with models allows us to develop that one step further, and then discussing those models in a group. We either come up with analogies when we're doing that, or we come up with questions when we're doing that then stretches our mental picture, and then we try to add a little bit to it by using it. But so my PhD advisor, he is a very good astrophysicist, and one of my very vivid memories of talking to him when I was a student was he would be like, imagine I'm an electron and I'm moving through this space, and I'm like, so he would embed himself in whatever the case might be, like gas swirling around a black hole, and he imagined he's an electron in that gas. And we had these like really fruitful conversations, and slowly, of course, through these conversations, I started developing that mental framework, and then I extended it, and then with my students, I'm developing maybe new things. So, yeah, our brains are capable of that, and like solving mathematical equations, you don't see them as numbers, you see the patterns in that equation. Like you just develop, I think, higher and higher frameworks.
Over to Van. We'll go 2 more questions, and I think we'll be out of time. Yeah, go ahead. First, go to Van first.
So, when observing the event horizon, you said that like the telescope you needed had to be the size of Earth, and I thought that was kind of lucky, because if it needed to be bigger, you'd have to use satellites and try to transfer that data down to the surface, which I assume would be a difficult task.
Yes.
So I was wondering, does that have to do with, like, since we're on Earth and we're trying to observe it from here, or is that more of just kind of like a happenstance that from the distance and the resolution you want it, that it just so kind of lines up that it happens to be the size of Earth?
It's the latter. So we said from the distance of these black holes and the mass that we know of them, so a size for their event horizons, what is the resolution that we need? And it just so happened that for the biggest 5 black holes in the sky, and by biggest, I don't mean biggest mass, I mean just the right combination of how close they are to us and how massive they are, which is the bigger size in the sky. Several are reachable by telescopes that we put on Earth. The remainder requires a satellite in orbit, a satellite on the or a dish on the moon, etc. So we said, since there are 3 or 4 that we can reach the horizon scale for, it's worth building this, and then we'll go from there. We'll do space-based interferometry. But exactly, I mean, you're very, very astute in what you described. The data that you have to transfer down then, what you would have to do is crunch it on board and then transfer. I mean, there's just no way. I mean, I'm saying we're FedExing literal disks. So that's not going to be possible. So some level of data crunching will need to be done on board, and then telemetry down to Earth. So we're not there yet, but if we want to look at more distant, smaller black holes, then that's the direction we'll go. But it's serendipitous that at least like we can do a few.
Maybe when we get 8G or whatever, 9G, it won't be a problem. I remember my dissertation was literally on floppy disks, and I had to carry now that's, so yeah. That's
Yeah. I mean, I certainly didn't have a supercomputer. I would wait until everybody went home. I mean, they knew about this. I wasn't doing it behind their back. Then I would log into every machine in the department and submit like pieces of the computer model that I wanted to run until they came back in the morning, and then just stop them, get my data back. And now, of course, we're like, oh, here's my several $million-dollar supercomputer.
You were that grad student.
I was that grad student. Yeah. I was like, when are you leaving? Can I run on your machine?
Yeah, that's good. Yeah.
So I was wondering, what makes Arizona such a prime candidate for a second telescope? Because wouldn't it be more helpful to put in a place that doesn't already have one to help diversify the data?
Very good question.
For the Kitt Peak.
Why do we need Kitt Peak? So we said effectively what we're doing with these pairs of telescopes scattered across the globe is collecting different notes of the music or different wavelengths of the image that we want to build. And even though the longest baselines, the longest distances between telescopes provide us with the finest details, the short distances are also necessary. They provide us with the bigger picture. So you go from, ideally, you would have everything from Kitt Peak to Mount Graham distance to here to maybe New Mexico, and then here to Mexico, here to, so you would have this ladder of all pairs of possible distances to cover the Earth. That is not possible, but Kitt Peak to Mount Graham turns out to be super useful.
Well, I want to thank you for taking time after the lecture. It's already late. And
My pleasure. This is always a great group.
And
Thank
I want
you
to
for
thank everybody here
for
for
your
some
questions.
Great questions. And this is we'll be back with episode 3 next week with Professor Joellen Russell. We're going to be shifting from black holes to our planet.
Yeah, what do we know
Yeah.
about climates? How do we know what we know about our climates? Yeah, it's going to be fun.
All right, thank you,
Yeah,
and we'll see you
thanks.
next week.